Welcome, everyone. Today, we're looking into something absolutely vital, something that powers, well, everything around us, but we hardly ever notice it. We're talking about power system frequency. We've got some great material here, a detailed presentation, and we're going to try and make sense of it all for you.
And it really is fundamental. If you want to understand our energy infrastructure, you kind of need to get your head around frequency. It's like the invisible conductor keeping the whole electrical orchestra in sync. You don't see it, but without it, well, things would fall apart fast.
Right. So let's start right at the beginning. The presentation mentions that frequency itself, just the concept, has no physical meaning. It's a property of a signal.
That sounds a bit abstract for something so important. What does that actually mean?
Yeah, it's a good place to start because it trips people up sometimes. Basically, frequency isn't something you can, hold in your hand. It just represents how often something repeats itself over time. The number of cycles or oscillations per second, usually.
Okay, like counting waves hitting a beach. Exactly like that. Or a pendulum swinging back and forth. How many swings per minute? That's its frequency. So while we can measure the frequency of physical things, like a spinning generator shaft, the frequency itself is just that measurement, that number. It's derived. And as the slide shows, we measure it in hertz. Hertz. 1 hertz just means 1 cycle happening every second. Simple as that.
Got it. So it's a rate, a count of repetition, not the thing itself.
Yeah.
Now, how does this abstract idea connect to the very real electricity flowing through our wires, specifically alternating current, AC?
Right, AC. In an electrical power system, the frequency tells us how fast that alternating current is. Well, alternating, changing direction. To really see it, you have to look at how AC power is made, which the presentation lays out nicely. It usually starts with steam, right?
High pressure steam, yeah.
Exactly. High pressure steam blasts against a turbine, making it spin really fast. That's converting heat energy into rotation. This spinning turbine is connected to the generator's rotor. That's the part that spins inside.
And this rotor is basically a big magnet.
Essentially, yes. When it's energized, it becomes a powerful electromagnet with north and south poles, and it's spinning inside the stator, which is the stationary part. The stator is lined with these heavy-duty copper bars, all arranged carefully.
Okay, so spinning magnet, stationary copper wires. I feel some physics coming on.
You got it. That's electromagnetic induction. As the rotor's magnetic field sweeps past those copper bars in the stator, it pushes the electrons in the copper, creating an electric current. But here's the key bit for AC. Because the rotor is spinning, the direction of the magnetic field crossing each copper bar changes constantly. North pole passes, then south pole passes.
So the push on the electrons changes direction too.
Precisely. It reverses direction twice for every full revolution of the rotor.
Yeah.
That constant back and forth flow is alternating current. And the presentation also points out there are usually 3 sets of these copper bars in the stator. That gives us 3 separate AC outputs or phases.
The red, yellow, blue phases you sometimes hear about.
That's them. Using 3 phases is just much more efficient for transmitting power over long distances. So the electrical frequency is simply measuring how fast this whole AC cycle repeats. And it's measured in hertz, the classic example like in the slide. A generator with 2 magnetic poles spinning at 3,000 revolutions per minute, that generates electricity at exactly 50 hertz. There's a direct link between mechanical speed and electrical frequency.
That makes sense. Mechanical rotation directly translates into electrical oscillation. So we have all these individual generators making AC power. Then they're all connected together into what the presentation calls a synchronous grid, and states very clearly, there can only be one frequency across that entire grid. That sounds incredibly strict. Why? What happens if you try to mix frequencies?
Oh, that would be chaos. Utter chaos. It's strict because that single unified frequency is the grid's master clock. Its heartbeat, like the presentation says, it ensures everything is in sync. Think about it. Every single device plugged in, from huge industrial motors to your phone charger, is designed expecting that specific frequency, 50 hertz here in Europe, 60 hertz in North America.
So if different parts had different frequencies.
It'd be like trying to run a complex machine where all the gears are spinning at different incompatible speeds. Things would break, motors would overheat or stall, protective devices would trip thinking there's a massive fault, transformers could saturate. It could lead to cascading blackouts very quickly. That single frequency is the fundamental coordinating signal for the entire system.
Wow. Okay. So it's not just about things running smoothly. It's about preventing catastrophic failure.
Yeah.
The heartbeat analogy is really fitting then. If it's the heartbeat, it must also tell us something about the health of the system, right? Like supply and demand.
Absolutely. Frequency is, in real time, the single best indicator of the balance between electricity generation and electricity consumption across the entire grid. The diagrams in the presentation show this perfectly. If generation is greater than the load, we're making more power than we're using, there's surplus energy.
And that extra energy has to go somewhere.
Exactly. It gets stored momentarily as increased rotational energy in all the spinning generators across the grid. They literally speed up just a tiny bit, and that makes the grid frequency rise.
Okay. And the opposite, if load is higher than generation.
Then the grid is trying to supply more energy than is being put in. That energy deficit comes from the stored rotational energy of the generators. They slow down slightly, and the grid frequency drops. It's a direct physical consequence of the energy balance, which is why operators watch it like a hawk.
And they try to keep it within a specific range, the frequency band, like 49.90 hertz to 50.05 hertz for a 50 hertz system.
That's right. That's the normal operating tolerance. They constantly work to keep it within that tight band. This leads us straight into frequency deviation. You have your target, the scheduled frequency, that's your perfect 50 hertz or 60 hertz.
The ideal.
The ideal, yes. Any difference between the actual frequency at any given moment and that target is a deviation. So if the grid is running at 49.95 hertz in a 50 hertz system, that's a minus 0.05 hertz deviation. Not huge, but noticeable to the control system.
And the main goal is just keep those deviations tiny.
Tiny and brief. That's what tight frequency control is all about. It's crucial for stability. This involves complex automated systems constantly monitoring the frequency and signaling generators to increase or decrease their power output, sometimes within milliseconds, to match the changing load and nudge the frequency back towards the target.
It really is a constant balancing act then,
Yeah.
happening every second of every day. But the presentation makes a point of separating normal variations from abnormal ones.
Yeah.
So some fluctuation is okay.
Oh, absolutely. You couldn't possibly keep it perfectly locked at 50,000 hertz all the time. That's impossible with millions of devices switching on and off randomly. Normal variation, as the slides show, is usually within an even tighter band, often called the dead band, maybe plus or minus 0.03 hertz around the target.
So for 50 hertz, that's like 49.97 hertz to 50.03 hertz.
Exactly. Little ripples like that are happening constantly. It's just the normal breathing of the grid as loads change slightly. The control systems generally don't react strongly within this tiny deadband. It's considered acceptable background noise.
Okay, that's the normal breathing. What causes the system to gasp then? What triggers these abnormal frequency deviations?
Those happen when something significant and sudden occurs. The classic example is losing a large power plant unexpectedly. Maybe a big generator trips offline due to a fault. Or perhaps a major transmission line fails, suddenly isolating a region, or a huge industrial plant unexpectedly shuts down or starts up. These create a much larger, faster imbalance between generation and load.
And the consequences of those bigger deviations are more serious.
Much more serious. Now, the grid is designed to be resilient. Even after losing a large generator, the frequency might dip significantly. But automated responses usually kick in fast, and it often recovers back towards the target, say 60 hertz, within a few minutes. But if the deviation is too large or lasts too long, that's where the danger lies.
All large is too large.
The presentation highlights a critical threshold. Deviations getting close to, or exceeding, plus or minus 1 hertz. So below 49 hertz or above 51 hertz in a 50 hertz system, that's getting into the danger zone. At those levels, you risk actual physical damage.
Damage to what? The generators.
Generators, yes, but also turbines, transformers, and even sensitive equipment on the consumer side. Large industrial motors are particularly vulnerable. They're designed for a very specific frequency. Running them too far off frequency can cause overheating, severe mechanical stress, vibrations, potentially leading to catastrophic failure. Even some home appliances or sophisticated electronics aren't designed to handle wide frequency swings.
So it's not just inconvenience, it's potential widespread equipment damage.
Exactly. That's why there are layers of automatic protection systems designed to disconnect generators or shed load, meaning intentionally cut power to some areas if the frequency deviates too far to prevent a total system collapse and limit damage. It's a last resort, but sometimes necessary.
It really puts into perspective how intricate and, in some ways, fragile this system is, that we rely on so completely. This whole discussion, It really paints a picture of frequency not just as a number, but as this dynamic, critical indicator, this invisible force holding everything together.
It absolutely is. It's the unsung hero of the power grid. The precision required, the constant adjustments, the sheer scale of coordination. It's a massive, ongoing engineering feat.
So we've gone from the abstract idea of cycles per second to the very real heartbeat of our electrical world. An amazing journey.
Indeed. And, thinking of the future, with more renewable sources like wind and solar coming online, sources that don't have the same inherent rotational inertia as traditional generators, maintaining that stable frequency becomes an even bigger challenge.
That's a really interesting point. How do we keep the heartbeat steady when the energy sources themselves are more variable?
That's the multi-billion-dollar question engineers are tackling right now. It involves new control strategies, energy storage like batteries, advanced forecasting, and making the grid smarter. So maybe the next time you flick that light switch and it just works instantly. Spare a thought for that incredibly precise 50 or 60 hertz pulse, that silent, steady heartbeat, and all the complex systems working constantly unseen just to keep it beating right on time. It's quite something.